Okay, welcome to lecture here. We're continuing on chapter 19, I believe. Let's get everybody in. Okay, so in chapter 19 here, we talked about a couple of things. We talked about transition metals. So we talked about some of the properties of transition metals, including electron configuration, also some of the sort of trends, if you will, in terms of transition metals, things like ionization energy, electron affinity, and so forth. Again, hopefully a lot of that was reviewed for you. It's, again, some stuff obviously you probably covered a little bit in, I would assume, Chem 50. Then we really got into sort of the heart of the rest of this chapter here, which is really coordination compounds. Coordination compounds are really two parts. Let's see here. We go. So one part is a complex ion. And the other part is a counter ion. So you can kind of think of sort of our coordination compounds as almost like ionic compounds. So when we have an ionic compound, we have kind of a positive and negative guy that sort of balance each other out in terms of their charges. And the same thing happens here. So we have a complex ion that, as we talked about a number of times, is basically a metal. A lot of times it's a transition metal, and it has a number of ligands that are attached to it. Again, ligands being Lewis bases, electron pair donors in that case. And then we have a counter ion, which is really just there to, again, really balance out the charge. And as we talked about last time, as we will see today, the complex ion as a whole can be positive, and that would mean that you would need a negative counter ion to balance out the positive charge of that complex ion. You can also have a negative complex ion overall, which would then mean that you need a positive counter ion to balance it out. Coordination compounds are also written like ionic compounds, which means it's always the positive guy first, followed by the negative. So again, the first guy could be a complex ion, or it could be a counter ion, and the same thing here for the second guy, as we'll see when we see some of these formulas here in just a bit. We touched upon a little bit more about some other pieces of information about complex ions. We do have those ligands, and those ligands can be what are referred to as being monodentate, bidentate, or polydentate. And what that essentially means is, as we talked about last time, that means that, you know, there are certain ligands that have the ability to bind to the metal in more than one place per molecule. So there's something like a bidentate one has the ability for every one of those ligands to basically attach into the metal at two different locations per one molecule of ligand. Monodentate means that they only really have the ability to bind in at one place per ligand, and polydentate, as we'll see, again, can bind in at multiple places per ligand. Now, that's really important for what we talked about, which is coordination number. And coordination number is the number of basically ligand atoms that are directly bound to the metal in a complex ion. So if you have a bidentate ligand, for every one of those, you basically get kind of two for the coordination number, because two of them can attach to the metal. For every monodentate, you get one that basically can attach to it. And that's really important because, as I mentioned last time, as we'll see today, sometimes people often fall into the trap of, you know, if they have like a metal and in the formula, you know, maybe it's like, you know, some type of ligand, and there's like a number down here, like a 2. And they go, okay, well, there's 2 ligands, so the coordination number is going to be 2. And again, that's not always the case, because if this happens to be a bidentate, it definitely will have to double that coordination number. So the coordination number, again, is not how many total ligands there are, but it really is how many atoms in those ligands are directly attached to the metal in the complex ion. We also talked a little about in this, I think where we sort of finished up was on a conversation of basically how do we kind of maybe guess what the coordination number would be, or some ways we could sort of figure that out. And we kind of finished up on this this little guy here that we have a charge of +1. Usually a lot of times you're going to end up with a coordination number of 2. Occasionally you can end up with 4, as you see. For a vast majority of guys with +2s, 4 and 6 are very common sort of coordination numbers that we end up with. And when we get to +3s, we can get up to a coordination number of 6. Again, they're kind of more deficient in electrons, which means they're able to basically attach more electrons or gain more electrons. So that's sort of why we see the coordination number go up as the charge goes up. Something that we also talked about in an earlier chapter when we talked about Kf, which again is that equilibrium constant for complex ions. A reminder that basically what happens is the ligands do attach basically one at a time. So it is a stepwise fashion, as we talked about. So, you know, if you had something like silver, you know, the first thing that would happen is we'll attach one of these guys. And again, that could have a K value associated with that. The next thing that would happen is we would attach, say, another one to it. Also would have a K value. And again, like we saw in chapter 16, we could add all these up together and get the Kf by multiplying these together for the formation of, say, adding 2 of these guys to it. So just keep that in mind. Again, maybe not too critical here in this chapter, but these ligands do really come on, again, one at a time. And they just don't all sort of pop on all at once. Any questions on that stuff we talked about last time? Okay. So here's just a couple of pictures of some of our complex ions and some of our ligands. This is ethyl endyl diamine. This is the guy that is abbreviated EN. So you will see that EN abbreviation, and they will use this EN abbreviation both in formula and also in naming as well. So instead of writing ethyl endyl diamine, people oftentimes will again use that little symbol. It is a bidentate ligand because at both of the nitrogens, it's got a lone pair, it's kind of polar there. And again, each of these guys would bind to the metal through the nitrogens. And again, you get a 2-for-1 type of deal here. For every one of these EN molecules, you do get 2 binding to the metal, and that would affect the coordination number. Over here is EDTA, ethyl diamine tetraacetic acid. It's a big name there. We'll see it in just a bit. But this particular guy actually binds in 4 different places. So 1, 2, 3, 4, 5, 6 places. I'm sorry, 6 places I meant to say. And you can see for every one of these EDTA molecules, you basically get almost a coordination number of 6 for every one. And it binds really, really strongly to a metal because it basically can surround it, right? And you can kind of see the metal's trapped in the middle. Over here, again, is a metal with a bunch of RENs attached to it. So in this case, this would be a metal that has En to the 3, would be like the formula would look. And again, the coordination number here, though, would be 6 in this case. Again, 1, 2, 3, 4, 5, and 6 being attached there. So again, not always going to be that number you see in the formula on the bottom. It does depend on the coordination number of the actual ligand. These type of ligands are sometimes referred to as being a good chelating agent. Chelating agent is really something that can basically surround and grab up like a metal. So obviously something like EDTA is a really good one, as it could bind 6 different places per every 1 molecule. And it basically is able to put a net over the metal and it grab it up pretty good. You'll actually see it if you look on some ingredient labels on things. You'll sometimes see that EDTA is on something. And again, it's usually used to grab up metals and that type of stuff. Here's a table, not from your book, but you have a similar type of table, I think. And some of the monodentate, against some people call them unidentate. But basically all these guys here basically will bind in 1 place per molecule. So we have something like water, cyanide, ammonia. Again, all these guys are kind of polar. They have those non-bonding electrons that are there on the atoms that are able to do it. Thiocyanate is, well, hydroxide, and then all of our halogens, you know, like Cl minus, Br minus, etc. Those guys are all monodentate again, basically giving you a coordination number 1 for everyone that attaches. Here are some of our bidentate, and these are 2 of the common ones that we sort of touched upon last time. There's our En, which is our ethyl endyl diamine, again attaching at the nitrogen in each of these locations. And this is oxalate that I think I drew the other day. And it also can attach at 2 places per molecule, and it's at the single bonded oxygen as to where that binds, kind of having a formal charge of -1 at that point, so it's able to kind of bind in there. So these guys, again, give you sort of a coordination number of 2 per molecule. This guy obviously is 1 per molecule. And polydentate can be multiple bindings per molecule. So as we can see here, we have this guy here, which is almost like En, but it's diene, and it basically has an extra nitrogen in there. So we have 3 places where this guy could bind. So coordination number 3 for every one of those. And then obviously here's our EDTA, our ethyl endyl amino acetic acid, basically. And again, that's those 6 different locations where all those arrows are pointing here. That is where it can bind. So like a coordination number here of 6 in this particular case. Any questions on that there? And here, just another picture of it. And again, kind of a picture of EDTA, and you can see it really does grab it up pretty tightly. As you get 6 binding per molecule in this case. All right, so why don't you take a moment here and let's, what is the oxidation numbers of each of the metals in the complex ion part? And what is the, let's do coordination number as well. And by the way, when something is written like this, typically the guy in brackets is the complex ion. So the complex ion is typically the guy in the bracket part. So figure out the oxidation number on the metal that's in the complex ion, and then also the coordination number that you got going on here. See what you come up with. Okay, so let's take a look here. Start with the first one, which is this guy here. So we have K, AU, OH, 4. All right, so as I mentioned before, typically when we write these formulas of our coordination compounds, usually these guys in the bracket is our complex ion. So this is our complex ion part. This means that this guy here would be our counter ion in this particular case. So if we want to figure out what is the basically oxidation state there on the gold, if we look at it here, Well, we have hydroxide, which is -1, and there's 4 of them, which gives us a -4. Coming out on the outside, we have a potassium, which is normally +1. So we have -4 and +1. Remember that when we have a coordination compound, it's always the positive guy, then the negative guy. And very much like an ionic compound, they do need to balance each other out to 0. And that means that the gold here should have an oxidation state of +3 in this particular case. So the gold should be a +3 in terms of the oxidation state. First off, any questions on that? Now, in terms of coordination number, we are going to be looking at really just the complex ion part here. And since OH is a monodentate, again, OH looking like this. Again, it is just the oxygen that's going to bind in there, which means it's monodentate. And there's 4 of them, which means the coordination number here would be 4 in this particular case. Any questions on that part of that there? Now, if we look at what's going on here, our counter ion here is +1, so we really have a potassium with a +1 charge. That means that our whole complex ion part, if we broke it apart, has a -1 charge overall. And that's because the gold is +3. All of the hydroxides are -4, gives us a -1 charge overall in our complex ion. And that's why we only need 1 potassium here to balance out the charge. +1 and -1 gives us no charge when we put it together. And that is basically what we can do here. So in this particular case, our complex ion is the anion, or the negative guy, and our potassium is the cation in this particular case. Any questions on that there? So let's take a look at the second one. So for the second one here, we got CrNH3 and NO3 to the 3 here. And in this particular case, we do see that our complex ion is the first part. So this part here is our complex ion. The NO3 here is our counter ion. And if we kind of take the same approach here to figure out, what is the charge on everybody, if we take our NH3, our NH3 has no charge, right? It's neutral. NO3 minus on the outside on our counter ion is -1. And there's 3 of them, which gives you a grand total of -3 in this case. That means to balance out all of the charge here, our chromium has to also be +3 in this case. So the chromium should have an oxidation state of +3. Here, the coordination number would be 6 because we basically have a chromium that has 6 of these ammonias basically attached to it. And ammonia is also monodentate. Again, if you draw ammonia, it is going to attach here at the nitrogen. So since there's 6 of them, that gives us a coordination number of 6. Any questions on that so far? Now, looking at this, we could actually see that our complex ion is actually positive in this case. And that's because we have 3 of our counter ions, which are -1 each. So that's all a -3. That means that this overall thing is going to be +3. coming from the chromium here. Again, +3 and -3 gives us no charge for our coordination number in this particular case. Any questions on that? So even from just looking at the coordination number or the coordination formula, you could determine, is your complex ion positive or negative, because here is our coordination number, our counter ion that comes first, so that means that's positive. Complex ion comes second in the formula, that's going to be negative. Opposite here, complex ion comes first in the formula, which means overall it's going to be positive. Comes second in the formula, that guy will be negative. So just like an ionic compound always has that kind of positive guy first, negative guy second, same sort of thing happens here with coordination numbers, or coordination compounds. Any questions on how to identify oxidation states, coordination numbers, and that type of stuff? Okay. So then let's talk about actually naming these guys. And to name these guys, it does take a pretty big name. A lot of them do have. So a lot of them have a relatively large name. And here are some of the rules that you kind of need to follow. So as I just mentioned before, the cation or the positive guy always comes before the negative guy. And that is both in formula and also, again, in name. Within a complex ion, so with the complex ion part of the coordination compound, we name the ligands first in alphabetical order, regardless of prefix. So if there happens to be a prefix, we don't look at that. We actually look at the first letter of the name of the ligand, and we put it in alphabetical order. We always name the metal part last. Now, what that means is whatever part of the coordination compound you're naming, as we just saw, the complex ion part could be in the first part of it, or it could be in the second part of it. So in the part of the name that involves the complex ion, you always end with the complex ion with the metal that's there as the last part of the name. We do change some things in terms of their ligands to O in terms of how they're named. So for example, water is aquo. Aqua is water as well. So some people use aqua, some people use aquo. Sometimes we do change the O at the end of it. Some neutral guys are usually called by the name of the molecule. There are some exceptions. So there are things that have sort of special names. So we don't call it ammonia here. We do call it amine. CO is carbonyl, we call it. Again, aqua or aquo for water. So there are some special names of certain ligands, and we'll see a table of that in just a bit here. Now, if we happen to have more than one of those ligands in the molecule itself, we do add prefixes. So if we had, say, 2 waters, we would add di to it, or tri if we had 3, tetra if we had 4, penta for 5, hexa for 6. So again, 2, 3, 4, 5, and 6. Now, if you happen to be lucky enough to hit a ligand that actually already contains one of those prefixes in the name, then we go with some different prefixes, bis, tris, tetrakis for 2, 3, and 4. So an example of that would be something like that EN. That is basically ethyl endyl diamine as part of the name. So that diamine part, ethyl endyl diamine, since the actual ligand itself has a prefix in it, we wouldn't use di, tri, tetra if we had more than one. We would use bis, tris, or tetrakis. In addition, a lot of times people will use these guys for something like oxalate as well. And that's our C2O42 minus, just sort of historically done, even though it doesn't really oxalate, doesn't necessarily have a prefix in it. People commonly will do that as well. Now, the oxidation number of the metal is always written in Roman numerals, so we do really kind of name coordination compounds almost like type 2 ionic compounds. And type 2 guys, you use those Roman numerals to indicate the charge, right? So, you know, whatever it may be, 3. And that comes after the metal name. And it also is used for things that we normally don't use it for in normal sort of nomenclature. So if you remember, you probably learned that silver has a fixed type charge, right? And silver is always +1, which means usually when we write something with silver, we don't actually put a Roman numeral, but here we actually do. So in the coordination compounds, we do use those Roman numerals for things like silver, things like zinc. So some of those guys that we normally don't use it for, we actually do use it for here. Also, another sort of weird thing that sort of happens with coordination compounds is you could actually end up with a metal that has a oxidation state of 0. Kind of no charge. And oddly, we usually use not really a Roman numeral, I guess, but you would still kind of put the 0 in parentheses. So that's kind of a weird thing that it kind of develops sometimes here in coordination compounds. Believe it or not, the oxidation state of a metal will end up being something like 0. So odd as it sounds, we kind of include that as well, usually in these guys when we go to name them. So those are two kind of different things than kind of normal naming that we've done, or you maybe have done before. The last kind of funky thing going on here with naming of these guys is if the complex ion part of your coordination compound is an anion or negative, we actually will not use the name of the metal like we normally would off the periodic table. We kind of will go old school on it. So perhaps you remember maybe when you learned about naming that perhaps, you know, things like iron are sometimes called ferric or ferrous. You know, something like copper is like cupric or cuprous. So sort of we use these sort of older ways of naming it, of the metal, and we put 8 at the end of it. So copper would be cuprate, iron would be ferrate. So sort of that older way of naming the metals with 8 at the end is sort of how we name metals in coordination compounds. And again, that is only the case where the metal is, or the complex ion part is actually negative in that particular case. So that's a lot of really kind of funky things going on here in terms of these namings. But just to give you an idea, for example, we had just kind of see how one works here. We'll go back to this guy here. So we'll just we'll go with this guy on the right since we got some room to kind of work with here. So if we look at this coordination compound here, we're going to start with our ligands that are attached, and it is ammonia. And ammonia, again, is what is referred to as amine. So we do name it amine here. And there are 6 of those ligands, as we talked about, and prefix for 6 is hexa. And at this point, we do have chromium here, which is our metal. Our complex ion part is positive, so we could just use the regular name there. So this is something like hexaamine chromium, Roman numeral 3 for the charge on the chromium. And then our counter ion is usually just named kind of like normal in an ionic compound, even though there's 3 of them. We just call it by its name. So NO3 minus is nitrate. So this would be nitrate in this particular case. So that's hexaamine chromium 3, which is our complex ion part, and nitrate, which is our counter ion, would be the name of this guy. Now, if we looked at this guy would be a little bit different. Again, go here, so I got somewhere to write it. So we had K A U O right? 4. Now, this guy is going to be a little bit different because as we can see just from the formula, our counter ion is our positive guy. Our complex ion is actually negative, as we saw. So we're going to start the name with just the counter ion. So we would just call the counter ion just its whole name, just like normal. Even again, if there was more than one of them, we would just call that potassium. So now if we sort of dissect our complex ion part, we really have just one type of ligand that's present, and that's hydroxide. And hydroxide, as we'll see shortly, has a special name known as hydroxo. There's actually 4 of them. So the prefix for 4 is tetra. So putting that together, we get potassium tetra hydroxo. Now what comes next is we're in the complex ion part of the name. We want to take the metal and name that at the end. But because our complex ion is negative here, we would not use gold in this case because it is, again, a negative one. We would use the old school name of it with the 8 at the end, and that's R-urates here for gold. So I'm just going to write it underneath as I'm running into the picture here. And that would be R-urate, and the coordination number, not coordination number, the oxidation state on that is 3, and that would be 3. So potassium tetrahydroxo R-urate 3 would be the name of that particular guy when we go to name it. Any questions on that? So that's the situation where you would want to use the older school name for the metal, is when the metal in the complex ion is part of a complex ion that's negative. And that is why on this one on the right, we just used a regular name of chromium because the complex ion was positive. Any questions on that? Okay. So let's take a look at some of these guys here in terms of some of our ligand names and some of our metal names. So here again, you can see these are some special names for certain ligands. Aqua, again, some people even go with aquo as well. Amine for NH3, methylamine, which is kind of what that name really is. Carbonyl for CO, nitrile for NO. And then our sort of halogens are named just like they kind of are in organic chemistry: fluoral, chloral, bromo, iodo. We just saw hydroxo. Cyano for cyanide is the name of it. Here's a table of some of the older ways of naming some of these metals. And again, this would be a case where the complex ion part is negative. So iron would be ferrate, cuprate, plumate, argentate, R-urate, and stannate for tin. So again, if you're sort of a little bit familiar with sort of the older way of naming those guys, we just kind of use that and put 8 at the end of it. Here's another table, and again, you should have a similar tables in your book, or you can refer to these, obviously. But some of the names we saw here, some other ones are fun, I suppose. Carbonate is carbonato, nitrite is nitro, oxalate is oxalato. I feel like you're ordering a drink at Starbucks or something like that. So some of these guys have some interesting names. Again, this one as well, as I mentioned, even though it doesn't appear to have sort of a prefix in the actual name, this is the one where people commonly do use bis, tris, if there's more than one of those guys in there. Waters are aqua or aqua. Here is our EN, so that is our EN guy that we saw. And again, sometimes people will actually just write EN, both in the name here and also the formula. And that's ethyl endyl diamine. And again, because this has di in the name, this is also another one that commonly bis, tris, etc. there is sort of used in terms of the prefix. This is our EDTA. That's our ethyl endyl diamine tetraacetic acid or acetate. And you can see it has a funky name as well. But again, instead of even using this for this guy, EN is commonly used as well. All right, so why don't you give it a go here and give this one a go. And what I'm going to do is I'm actually going to, what am I going to do there? Let's take out this part of it here. Don't worry about this part. So just do, all right, so just do this part here. So take a couple of minutes. Okay, so let's take a look and see how we're doing on this one. So again, we're just gonna focus in on the part in the box there. So let's just kind of look at this guy. So the first thing that we really can sort of figure out just from looking at the formula here is this guy in the box is gonna be our complex ion. And obviously that by default would make this our counter ion. So right off the bat, we know our counter ion is the positive guy here. We know overall our complex ion should be negative. So we'll start with the complex ion part. We want to probably figure out our oxidation number here of our chromium. So when we look at C2O4, that is -2 because that's oxalate. That means that there is a -6 overall happening with the oxalate part. Potassium is +1, and there's 3 of them, which means there's a +3 happening here. And remember that we do want it to equal 0, so in this case, the chromium would be +3 in this case to balance it out. +3 and -6 is -3. And +3 is what we got on our counter ion. That means if we just sort of isolate the complex ion part, this is +3. Again, this is -2, -6. It has an overall charge of -3, our complex ion. And that is why we have not 1 potassium here, but we actually have 3 potassiums here to balance it out. So that gives us +3 and -3 gives our overall charge of our coordination compound of 0. So again, that's why there's 3 of the potassiums there to balance out the charge. Any questions on that so far? That also tells us that because the complex ion part is negative, we do need to kind of go the old school name here for chromium, and that's going to be chromate, ATE at the end of it. We also know that it will have a Roman numeral of 3, right, because of the charge on it. If we look at our ligand here, our ligand is oxalate, which is our fun name of oxalato, is the ligand name there. There is 3 of them, which gives you trioxalato. And at this point, we kind of have everything that we need. We could put it all together here. Again, we will start with our positive guy, which is our counter ion. And even though there are 3 of them, counter ions are really just named by what it is. So we would just do potassium. We would then start with our ligand for our complex ion in alphabetical order, since there's only 1, trioxalato, chromate, Roman numeral 3. So this would be potassium trioxalato, chromate 3. And as I mentioned before, some people will kind of use that other prefix here, and it's kind of specific for oxalate. So sometimes people will do tris oxalato chromate 3. I think it's just a kind of historical thing that people sort of use that. So for our class, I'll take either one for oxalate. You could do either one, but do be aware sometimes people will use that tris one with it. Any questions on that there? So in relationship to this, you know, if you were given just the complex ion part, so for example, if you were given just this guy, and you wanted to name this guy, you basically would just use the back part of the name there. So this would be trioxylato chromate 3. And because it's an ion, there's no counter ion, you just put ion at the end of it. So that's how you would name it if you just had the ion by itself. Basically use the same name, just leave off the part with the counter ion in there. Any questions on that there? Okay, lastly here, coordination number. Coordination number on this guy is going to be 6 in this case. So it is not going to be 3 like we see here. It is going to be 6. And that is because oxalate is this. And as we talked about, it is bidentate. So for every one of those, it's going to attach in 2 places, which means if we have another oxalate, I'll just draw the oxygens, that's going to be 2 more attached. And we have a third oxalate, it will also attach, giving us 1, 2, 3, 4, 5, and 6. So the coordination number here is going to be 6 for this particular guy. So again, because this is a bidentate, you do have to adjust it for it being basically 2 for 1 in that situation. Any questions on that there? These two, see what you come up with. So first one first here in the formula. So that implies that this guy is positive. Our counter ion is coming second, so it is negative. So that means we can use just a regular name for our metal. We do probably want to figure out the charge that's going on our metal. So water here is 0 in terms of its oxidation state, it's neutral. Cl is Cl minus, so that's -1 here, and there's 2 of them, gives you a -2. Our Cl on the outside is also an ion, which is -1. So overall here we have -1 on the outside, -2 for the 2 chlorines on the inside. That gives us a -3 overall. That means that our chromium here should be +3 to balance out. So putting it together here, we have a couple different ligands in this case. We have 4 water, so 4 is tetra. Water is aqua or aqua, whichever one you like. We also have 2 of the Cls, and that is dichloral. Di for 2, chloral for chlorine, and or chloride. And in this case, we are going to put these guys in alphabetical order. So alphabetical order in this case is regardless of prefix. So we have A versus C here. So it is actually going to be tetra, aqua, dichloral. Because our metal is in a positive complex ion, we just use the whole name of the metal, which is chromium, Roman numeral 3 for the charge on it. That takes care of the entire complex ion part. We are now left with just our normal counter ion here, and we name it just like normal, even if there was more than one. It is just called chloride. So tetra, aqua, dichloral, chromium 3, chloride. Any questions on that name there? Again here, the metal comes at the end of the complex ion part, not the end of the name necessarily, but the end of the complex ion part. And if you had just the complex ion by itself, what we're looking at is chromium 4 waters. We have 2 of these guys. Again, overall charge here is going to be +1 from the +3 of this guy, the -2 of that guy. And again, that is why we have just one of the counter ions, in this case, the chloride. We have just one of those guys. Any questions on that name or anything going on here? Coordination number of this guy would be 6 in this case. We have 4 waters, which are each monodentate, so that gives us 4. We have 2 CLs, each are also monodentate, gives us 2 more. Gives us basically 6 total going on in this case. Any questions on that there? Okay. So let's talk about then writing the formula for what we got here. This is tris-ethylendyl-diamine cobalt-2 sulfate. So first off, that ethylendyl-diamine is the thing that we can use as EN, sort of the abbreviation. So when we look at this, we do see that the metal with the Roman numeral here comes in the first part of the name. That implies that this part of it is our complex ion. And our sulfate here is our counter ion. So really just kind of building everything we have here from the name. We have a cobalt-2. So cobalt-2 means it's a cobalt with a +2 charge. We have tris, which is 3 ethylendyl-diamine. So that basically means we have 3 of these guys. And again, you don't have to write out the formula. You can just use EN. And that's basically our complex ion part. So if we put that together in our complex ion, we have a cobalt, we have 3 of these guys. So what we want to figure out is what is the overall charge here of our complex ion. And if we do that, our cobalt is +2, this guy is 0. That means that our overall charge of our complex ion is actually +2. And that's important because sulfate is our counter ion, and sulfate is SO4 2-. So what that tells us is we actually only need one of these guys to balance out the charge. So to do that, we would just use 1. So we'll get rid of that there and basically put in our 1 guy here. And this would be our coordination compound here, our COEN3 and SO4, just one of them there. Question on that? Coordination number here is going to be 6 in this case. Again, this EN is that ethylendyl-diamine that we saw earlier, looking like this. So for every one of these EN molecules, it will attach twice to our cobalt. So since we have 3 of them, we will end up with a coordination number of 6. Any questions on that there? Okay, so let's take a look. So we're going to do some names here. So again, looking at the first one, we see our bracketed guy here with our transition metal. There comes first. So that's going to tell us we're dealing with a positive complex ion. This is going to be our negative counter ion. So we do want to kind of just dissect what we got going on. We also want to figure out the charge on the cobalt here. So NH3, which is ammonia, that has no charge, so that's neutral, right? So that's 0, even though there's 5 of them. We do have a Cl, which is chloride, so that's -1. We also have a couple of chlorides on the outside. Each of them is -1, so that is a -2. So in this particular case, that's -2, and -1 is -3. That means here again, the cobalt is going to be +3. I know we ran into a lot of +3s in these. They won't always be 3, just so you know, but it happens to be. In this case, it will be 3. Also, because our complex ion is positive, that's going to tell us that we can just use the regular name for cobalt. So we do have obviously cobalt Roman numeral 3 here. We also have 5 of the ammonia, and that is known as pentamine. We also have 1 of the chloride, which is chloral, and that is all of our sort of complex ion part. We do want to put it together here in alphabetical order, ignoring prefix. So again, it is A versus C in terms of our ligands. So that's going to be pentamine, chloral, cobalt 3. That takes care of the entire complex ion part. What is left is our counter ion, which even though we have 2 of them, we will just call it chloride. So pentamine, chloral, cobalt 3, chloride would be the name of this guy. And again, on that counter ion, why we sort of name it like we would. So just like in like an ionic compound like this, CaCl2, this would be called calcium chloride. Again, even if we have more than one, still is chloride. And so that's sort of how these guys are named as well in a similar fashion. Any questions on that there? And again, if we look and just sort of isolate the complex ion part, we see that this has a +3 charge, this has a -1 charge. So our complex ion is overall charged +2. And that is why we have not 1 chloride, but we have 2 of them to balance out that charge. Any questions on that one there? Lastly, I guess coordination number here would be 6 for this guy. Again, 5 of the NH3s and 1 Cl minus there would give us a coordination number of 6. Now, looking at the second one that we got going on there, we see something sort of opposite here. We do have potassium, and we see our bracketed and transition metals on the second part of the formula here. So that means that our complex ion is going to be negative in this case. Our counter ion in this case is going to be positive. So taking our same approach to figure out the oxidation state of iron, Cn is Cn minus, which would be -1. There's 6 of them, gives you -6. Potassium is +1, and again, there are 3 of them. So again, oddly in all these examples, our metal is going to be +3. Again, won't always be +3, just happens to be. So we can kind of construct what we need to name here. So we do know that our iron is going to be +3. We also know that the iron is part of a negative complex ion, which means we will not use iron as our name. We go kind of old school on it. So that is ferrate, Roman numeral 3 for the iron part. We also have our Cn minus, which is cyano. And there are 6 of them, which is hexa. And kind of putting all this together, starting with our counter ion, again, even though there's 3 of them, it's just going to be potassium. We will then go with our ligand, so hexacyano, and then our metal at the end, ferrate 3 in this particular case. Now, if we isolate our complex ion part, just to kind of show you, how we got to our counter ion, iron here being +3, Cn being -1, gives us an overall -3 for our complex ion. That is, again, why we need not 1 counter ion here, not 2, but we need 3 counter ions to balance it out. And in terms of coordination number here, this would also be 6, as Cn is monodentate, and there's 6 of them. And lastly, in terms of the potassium part of the name, it is very much like if you had something like K3N, you would call this potassium nitride. So same idea here, even though there's more than one, same thing here. We just use really the name of it. Any questions on any part of those names or coordination numbers, oxidation states, putting that together? All right, then why don't you try a couple of writing some formulas here. So for each of these, write the correct formula and see what you come up with. Kind of just want to work through the different parts of the name and kind of put it back together, if you will. So first off, we do see here that in the first part of the name, we do have the Roman numeral and the transition metal. So this should be our complex ion part. Here we do have this guy, which then would obviously be our counter ion. So just kind of going through everything here, we have triamine. So that is 3 of the NH3s. So that takes care of that part. Bromo is bromide, so that is Br minus. Platinum 2, so that is Pt with a +2 charge. So that is all the parts of our complex ion, so we could kind of build it here together here. So we have Pt, we have a little NH3, we have a Br. So we want to figure out maybe what the charge is on our complex ion. So we have platinum, which is +2, 0 for the NH3, and -1 for the Br. That's going to give us a grand total of a +1 here for our complex ion. And that is why, obviously, we use platinum as the name, because our complex ion is positive. And that's important because, obviously, our counter ion is chloride, which should be Cl-. So we would just need Cl here. And that should be our formula here. Any questions on that one? Coordination number here is actually going to be 4 in this case. We have 3 ammonias and 1 bromide, giving us a coordination number of actually 4. Any questions on the name of that one? Okay, so here we're going to look at potassium hexafluoral cobaltate 3. So here we do see the Roman numeral here on the second part of the name with our transition metal. That means that the potassium is going to be our counter ion. That also means potassium would obviously be K+. This is going to be our complex ion. So cobaltate is cobalt with a +3 charge, which is what the Roman numeral stands for. Hexa is 6. Fluoral is fluoride. So you got 6 of those guys happening. So putting together our complex ion part, that should be everything. Put it in brackets. We got a COF6. Overall charge happening here, this is +3 for the cobalt. Each of the fluorides is -1. That is going to leave us a -3 left over. And that's important because that tells us we need not one of these K pluses, but we actually need 3 of the K pluses to balance it out. And that gets us to K3COF6. This being coordination number of 6 for each of the fluorides there. Any questions on that formula there? Questions on naming in general, writing formulas? You obviously need to be able to do both. Obviously, you need to be able to figure out things like oxidation states of the metals and the complex ions, and also things like coordination numbers and those type of things. Any questions on any of that naming stuff? Okay, I